Okay, in this lecture, I am going to introduce a very important concept, the concept of time temperature transformation diagram, or in short TTT diagram. Time temperature transformation, or TTT diagram. In short, or alternatively, it is also called as an isothermal transformation diagram. Now, what does this tell us? It tells us very neatly in a single diagram that under isothermal conditions of different temperatures, what would be the kinetics of transformation. So, if we have data for the kinetics of the transformation, then we can create such diagram. For example, if we know the Rami kinetics of a particular system, where see, Rami kinetics tells us fraction transformed as a function of time for a given temperature. Now, if I have the kinetics for many different temperatures, then I can put this entire kinetics into a single diagram, which very simply tells me how fast things are going to change at different temperatures and how long they are going to take and so on. So, let us see how we can relate the Rami kinetics, and from the Rami kinetics I will show you how we can create such diagrams. So, starting point is the Rami kinetics, which is fraction transformed, which is F is equal to 1 minus e to power minus kt to power n. Now, we are going to consider one phase transforming to the product phase. So, alpha transforming to beta. This could be, for example, iron FCC transforming to iron BCC as we lower the temperature, or it could be austenite undergoing a eutectoid reaction producing pearlite, alternative layers of ferrite and cementite, or any other transformation. So, let us see, let us consider a temperature. Obviously, we are going to consider temperatures less than the transformation temperature, where alpha can transform to beta. So, let me sketch first the Rami kinetics for a given temperature. So, I have my fraction transformed beta phase, this is my time axis, and let us say at some particular temperature, this is fraction 1, this is 0, and let us say this particular transformation kinetics given by this curve is at a temperature of T1, where T1 is less than the transformation temperature Tr. But we will keep this T1 quite close to the transformation temperature. So, we are first looking at the kinetics at a relatively high temperature with reference to the transformation temperature, and then we will consider other temperatures lower than T1 and see what happens there. Now, in this, let me mark out 2 points. One is, let us say, when the fraction transformed is 0.001 0,1 or simply 1% beta phase has formed, and let me mark one more point, 0.99 or simply 99% transformed. In a corresponding diagram, and here in this corresponding diagram, my vertical axis is going to be temperature and the horizontal axis is going to be time. My TR, let me also mark the transformation temperature TR. Similarly, let me mark the transformation temperature TR. With reference to the transformation temperature, T1 let us say is somewhere here. So, this is the temperature T1. This 0.01% transformed is many times considered as the start of the transformation, because it is really difficult to actually figure out exactly where the transformation really starts, because you can't measure very small quantities. So, very often we say that 1% is a point where the transformation starts, and similarly 99% is where the transformation is essentially over. So, now let me reproduce these 2 points in the temperature versus time plot here. Let me call these 2 points as A and B. So, I reproduce these points on this corresponding graph and call these points here as this point as A and this point as B. So, these are basically in this temperature time plot, A is representing 0.01 transformed, B is representing 0.99 fraction transformed. Now, let us consider another temperature less than T1. So, let us consider a temperature T2. Now, as would be expected, you remember that as we are reducing the temperature or increasing the undercooling, initially the rate of transformation will increase, it will go through a peak, and for much higher temperatures again the transformation kinetics will start to reduce. So, let us say T2 is a temperature where the transformation rate is actually increasing or in fact near the peak. Then what will happen to the Rami kinetics? The Rami kinetics would be much higher, which means this curve will shift to the left. So, let me plot a second curve showing the kinetics at temperature T2, and this is at a much higher rate. So, therefore, it is shifted to the left. This is at temperature T2. These 2 points on this represent 1% transformed and 99% transformed. Now, we copy these 2 points as well. Let me first mark these points as C and D, and let us copy these 2 points here, and let us say T1 is somewhere here. Oh, sorry, T2 temperature is somewhere here. So, if I copy point C gets copied here. I will call this C as well in this diagram. Similarly, reproduce D point also on this, and let us say this comes somewhere here. So, these are points C and D on the at temperature T2 corresponding to this particular kinetic behavior or the rate of transformation behavior. Now, let us consider a third temperature which is less than T2, and let us call that as T3. here that we have gone sufficiently low, the undercooling is large such that the rate of transformation has fallen down. In fact, the rate of transformation is even lower than the rate of transformation at T1. Then the third curve of Rami behavior at temperature T3 would now be to the right of this temperature T1, and hence this becomes my third transformation curve. Let me extend this line. This point corresponds to 1% transformed, and if I extend this line, this point corresponds to 99% transformed. Let me call these points as point E and point F, and I will reproduce these 2 points as well on the temperature time diagram, and let us say that this temperature T3 is here. So, reproducing point E would be here, reproducing point F, and this point would come here. So, if I look at these points carefully, particularly the points A, C and E, here A, C and E, these are 3 points which correspond to the condition where only 1% transformation is complete. Then the points B, D and F, B, D and F correspond to the condition where 99% of the transformation is complete. And you can imagine that I can draw many other fractions and I can keep transferring them, and then I can join all the 1% points together by a smooth curve. I can join all the points which are corresponding to 99% of the transformation complete together by a smooth curve. So, I can join A, C and E, then this will come out like this. I join B, D and F corresponding to 99% complete would correspond to a curve something like this. So, all the points on the curve ACE, so in fact even the intermediate points are corresponding to the points where 1% transformation is complete. All the points on the curve BDF correspond to 99% complete. Now, this is what is called as the time temperature transformation diagram or the TTT diagram. So, now what is this diagram telling me? So, let us say I have this alpha transforming to beta below the transformation temperature. Then if I look at let us say I am initially at a temperature above TR and I suddenly cool down very rapidly almost in 0 time, that I reach a temperature T1 and then I hold there, then I know that this much time will be required for 1% transformation to take place and this much time would be required for 99% transformation to be complete. Similarly, if I cool down from above the TR temperature to a temperature T2 here, then only this much time is required for the transformation to take for 1% transformation to take place, and while this much time will be required for 99% transformation to take place. Similarly, if I go down to T3 and isothermally hold there, I require this much time for the transformation to complete 1% and this longer time for 99% transformation to take place. Similarly, I could well hold on to some other temperature T and hold there, then this much time for one person to complete, this much time for 99% transformation to complete. So, what we have managed to do here in this TTT curve, we have taken all of this Rami data that we can experimentally obtain by as we had already discussed, that how we can do this by quenching samples in constant temperature baths like a salt bath, and then hold the samples for different times and then do quantitative measurement of the microstructure to obtain volume fraction as a function of time. Then we can obtain n and k data for different temperatures, and from that we can get these curves, and from these curves we can draw one single diagram which very readily tells us how the kinetics is going to take place at different temperatures. Now, this in a briefly is actually what the time temperature transformation diagram. Now, what would happen if I just cool down very rapidly, that I never touch these curves? As you can see that these curves are anyway going, and as we are going lower and lower in temperature, you require anyway very long time for transformation to take place. So, if I cool down so fast that I do not touch even this first starting curve of 1% transformation, then I can expect that no transformation should take place. Well, I can expect that no diffusional transformation can take place. In some systems, and a particular example of that is the steel system, the iron carbon system, where even if you do not touch these TTT curves, the austenite would then transform into a metastable phase called the martensite. On these curves, those starting martensite start lines and martensite finish lines are also put, which I will show a little later. Now, another important thing that I want to talk about is that here these kinetics we can get from these diagrams only if we are able to cool down very rapidly, and after that we have to hold isothermally. Though these diagrams are important, there are another set of transformation diagrams which find even greater importance in industry, because large number of heat treatments that are done in industry are not heat treatments like this, that you are at a high temperature, you cool down very fast and then hold at a constant temperature. In fact, most of the heat treatments, though this is done in many cases, but very many larger cases, industrial heat treatments would involve not a cooling in this fashion and then isothermally holding. It would be more like cooling continuously, so more like cooling like this. So, what can we do if we have a cooling characteristics which is a continuous cooling all the way down to room temperature? Can these diagrams help us then, the TTT diagram? Because the TTT diagram are valid only if you have a cooling regime or the heat treatment regime of this kind. Well, the TTT diagram can still help us. Where they can help us is that from the TTT diagram we can generate another set of diagrams which are called as continuously cooled transformation diagrams. or in short CCT diagrams. So, in the case of the continuously cooled diagrams, let me just redraw this a little bit below. Suppose I have cooled like this. It is possible then from the TTT diagram to generate these CCT diagrams, which I will show a little later. That suppose I want to know at what point along this cooling curve 1% phase would have transformed. Well, I can calculate, and it would be at a point somewhere here, a little lower and little to the right of this point. Similarly, if I had a cooling rate like this, then I would have transformed 1% somewhere here. Another cooling rate I would have transformed somewhere here, and in this way I can join another set of curves. This one corresponding to 1% transformed. Similarly, I would have got another one here corresponding to 99% transformed, while correspondingly these white curves corresponding to the TTT diagram, this is 1% and this is 99%. So, I would have got similar looking shapes, the shape of a C, or sometimes called as a C curve. Similar C shaped curves I would get for the CCT diagrams as well, and these are very, very useful diagrams when you are designing heat treatments. In fact, both of them, the TTT as well as the CCT diagrams, are useful when one is designing heat treatment to obtain desired microstructure and to obtaining desired mechanical properties or other properties. So, now the next thing what I will do is look at how to convert the TTT diagram to a CCT diagram, and in order to do that we have to understand a few things regarding this conversion, regarding the kind of transformation that would or rather the type of transformation determined by the Rami equation. It could be fairly simple for certain types of transformations, and it could be more mathematically more complex for other types of transformation. So, let us look at converting TTT diagrams to CCT diagrams. So, converting TTT to CCT diagrams. So, TTT when the isothermal heat treatment is being done, CCT when the material or the sample is continuously cooled. So, this is isothermal and this is non-isothermal. There is a widely used rule for converting TTT to CCT. So, first we will understand the rule and then we will see under what circumstances, under what conditions we can use this rule, and this is called as the rule of additivity. So, the rule of additivity, or called as the additivity principle, can be looked at in the following manner. let me just draw a schematic of TTT diagrams. Let us consider a continuously cooled material, and what we do is we approximate this continuously cooled behavior into small isothermal steps. That is, I discretize this continuously cooled curve in this fashion. So, I discretize this into large number of steps, and there are small isothermal steps, as you can see. Let us consider this to be, let us say, the ith step, and let me consider the temperature here as Ti. Let me consider the temperature of the previous step as Ti minus 1, and the temperature for the next step as Ti plus 1. Corresponding to these, to let us say Ti, there is a time Ti, and corresponding to Ti plus 1, there is a time Ti plus 1. The difference between these two times is the length of the isothermal step, and let us call this as delta Ti, which is nothing but Ti plus 1 minus Ti. Now, at this temperature Ti, if I had held the sample at temperature Ti, how long would it take, let us say, for the fraction to transform by, let us say, some fraction f naught? It could be 1%, it could be 99%, it could be 50%, whatever, but some fixed fraction. So, at fraction f naught, if this is the curve for the fraction f naught transformed, how much time it would take if I had to isothermally transform at Ti? So, I quench directly to Ti and then hold it. Well, that should be clear. The time would be this much. Let me call that time as tau, and superscript TTT, that this is the isothermal time at the ith step, or basically at temperature Ti. So, now the additive principle is as follows. That I take at Ti the fraction of the time spent, delta Ti, delta small Ti, fraction of the time over to the total time required for the transformation at Ti is delta Ti divided by tau TTT I. That is, this denominator is the time required to isothermally transform at temperature Ti, while delta Ti is the time spent in this particular isothermal step of the continuous cooling. So, now the rule of additivity states that if I sum up all these small fractions, so delta Ti upon tau I TTT, I going from the first step, starting right from the beginning of the transformation temperature, to let us say some step n0 such that n0 is that many steps required such that the sum of all of these small steps become equal to 1. Then we would say that along this cooling curve at the n0th step, the transformation of fraction F0 would have taken place. This is the simple rule of additivity. After that, I can simply add up all of these time increments of delta t1 plus delta t2 plus delta t3 all the way to delta t n naught. That would give me the time required at which fraction transform would be f naught. So, I add up all of this, and then as a result of all of these addition, I will end up at some point here, that this could be well the n0th step. So, this would correspond to the fraction transformed f naught if I go and trace along this cooling curve. Now, I will show you the calculation later, but we will take up one example to actually calculate certain points along different cooling curves using a spreadsheet to see how the shape of the CCT curve and how and at what position the CCT curve gets shifted. But before doing that, what I would like to now show is that under what condition this additivity principle is applicable. It is not applicable in general, it is applicable only in some specific conditions. So, let us quickly have a look at those conditions. So, the condition under which the rule of additivity, so validity of the additivity principle is very easy to state, that the additivity principle is valid for all transformations where the kinetic follows the following relationship: df by dt, the rate at which fraction transformed as per unit time df by dt, the rate of transformation should be a function like this. Capital G is one function which is a function only of the fraction transformed at that instant of time. H is another function, and this is purely a function of temperature. If the rate, kinetic rate, the rate of transformation follows such a general equation where these two can be separated as two separate functions, then it can be mathematically shown that the principle of additivity is valid. Now, I just want to examine, is a Rami relationship following this principle or this condition or not? So, let us start with the Rami equation. Rami equations is 1 minus e to power minus kt to power n. I take the first derivative. So, df by dt equals n k t to power n minus 1 times 1 minus f. This we have already done in an earlier lecture. now what I can do is I can, from this equation, I can write down, I want to eliminate time from this equation. So, from here I can write down an expression for time. An expression for time would simply be as follows: time is equal to 1 upon k to power 1 upon n times minus ln 1 minus f to power 1 upon n. Now, this is simply rearranging the terms in the Rami equation and writing it. So, first take logarithms and then write down an expression for time. This time then I can substitute here to get my rate df by dt as follows. I am going to directly write this, and then you can actually expand and actually show that this is indeed the case. This can be written as k to power 1 upon n times n times minus ln 1 minus f to power n minus 1 upon n times 1 minus f, and the square brackets closes here. Now, this particular term, let me call this, if I look at this, let me call this as, this is purely a function of f. It is also a function of n, by the way, but I am just writing it as a function of f. This, let us say that k can vary with time, temperature. If k varies with temperature, then this becomes a function of temperature. So, this relation, now I am trying to write it in this form. Now, when can I write it in this form? I can write it in this form when n is a constant. So, n is independent of temperature, and only k is a quantity that varies with temperature. So, all those Rami curves that I had shown for different temperatures could result if k is a function of temperature while n is a constant. Now, is this really true? Well, in many systems this could actually be approximately true, in the sense n represents a mechanism of the transformation. You know, whether the mechanism is heterogeneous, homogeneous, whether there is site saturation or not site saturation. If you remember, if you go back to the starting lectures, we had shown that if there is a site saturation, you get a certain value of n. If you have constant kinetics, you get a certain value of n, while k could vary. So, we could make statements on n. So, if we assume that this entire set, at many different temperatures of the TTT diagram that I have, if mechanism is the same, then I can say that n is a constant, and if n is a constant, then this is purely a function of f and independent of temperature, and k is the only one then that is left to change with temperature. Hence, this one is a function of temperature. Under this condition, then the Rami kinetics, and in fact all kinetics which follow this, are called isokinetic reactions. Okay, so now what we will do now is look at a example where we assume that n is a constant and k varies with temperature, so that we have an isokinetic reaction of one phase transforming to the second phase, and look at how we can, in Excel itself, in a spreadsheet, how it is possible to convert a TTT diagram to a CCT diagram. Here this is a little involved, so I already have a lot of data I have already input. This is for a particular plain carbon steel. Here we are looking at austenite to pearlite transformation, and what I have here is, in this column I have temperatures starting from just below the eutectoid transformation temperature and then going down to over an entire large range of temperature. Out here is the value of K, which varies as a function of this temperature. If we were to just quickly look at how K varies with temperature, well, I can plot. Incidentally, this K values have been obtained from data of TTT diagrams. Now, this K, if I make a scatter plot and let me just remove this formula box here for a minute. I insert, no, I have already, sorry, I click on this select data in the plot, add a graph, and first add the x values. My x values are going to be temperature, and then add to the y series the K values and click OK, and let us look at what kind of a graph I got. Well, wait a second, I did I plot till, no, the temperature I have plotted only up to 692. I must increase my temperature range in the graph. Let me just go to select data, edit, it somehow got clipped to 40, it should have gone to 356. So, this is going from C6 to 356, and the temperature values and the K values are going from A6 to 356. If I get this now, you can clearly see how K varies with temperature. So, you can see that as we are reducing the temperature, the K initially increases, goes through a peak and then comes down. This is also clearly showing that as K is increasing, our transformation kinetics is increasing, the rate of transformation is higher, as we already know, and as K reduces, the kinetics reduces, and this is to be expected. So, this is the behavior of K with temperature. Now, let us come down just a second, I will just get this out of the way and bring this formula box here to help us. Now, what I want to do, I have now K values, I have the temperature values, now I want to calculate the time, isothermal time for at different temperatures, that at, if I hold the sample at 726, how long is it going to take for the transformation to complete 0.01 or 1% or 50% or 99%. So, let us begin with the time calculation. Now, if you look at this first equation, this gives me the time of transformation, or what I had just written on the board, tau TTT, and this is nothing but rearrangement of the Rami equation, and I will just simply quickly put down this relationship, natural log of 1 minus the fraction transformed I am interested in is 0.01, and I will anchor it to row 4 divided by the corresponding K value at the temperature of 726. And this and this would have to be, if you look at this relationship, this will have to be raised to 1 upon n. So, cap representing to power 1 divided by, and I have the value of n here in column A2, which is 3.76, and I need to anchor it so that it does not change when I copy it to different cells. And I get a value of 14,548 seconds, so a long time. Now, I will just copy this time just a sec, copy and paste up to 376 and paste it to get now different times. So, as you can see that initially large time and the time is reducing, and if we keep going down, time is reduced to small values, and then now time starts increasing again as expected as we keep increasing the undercooling. So, as the undercooling is increasing, time is initially decreasing of the transformation and then increasing. All I have to do now to calculate the times for 50% and 99%, I will simply copy this column now. Whoops, I must have made a little mistake here. This is, yeah, I should anchor A6 in such a way that the column does not change, but the row should be allowed to change. So, I must put the dollar sign in front of A. I will just recopy this formula again in this cell, and that takes care of this. And then now let me copy this entire column and then paste it here. So, now we have the times for 50% transformation, and then similarly if I paste this one here, this gives me 99% transform. Now, if I were to plot this as now a TTT diagram, that means it will have to be temperature versus time. Well, I already have so as soon as I calculated the data, the graph shows me the 3 curves. The blue one is for 1% transformation, the red one is for 50% transformation, and the green one is for 99% transformation. So, this curve represents this data, the red line represents this data, and the green line represents the 99% data. Okay. So, now I have the TTT curves, I want to convert them into a CCT diagram. For this, I need to impose a cooling rate. So, let me keep a very simple cooling behavior of the sample. So, the cooling curve that I am going to describe here is time is equal to some constant B times the transformation temperature minus T. So, as so this is a linear relationship between temperature and time. So, I am just assuming a straight line, and if I put this formula here for a given value of B, so let us say B is 100, then the time would be H4. Now, this should be anchored so that the rho does not change, multiplied by the transformation temperature. Well, eutectoid temperature 727 minus T. So, this would be Tr minus T. So, hence I should start from, let us say 726, anchor this also such a way column does not change, and I get a value of 100, and I just copy this value down here and paste it here. So, I get these various temperatures or other various times at different temperatures. So, my cooling behavior, and if I were to show the cooling rate, well, this is how the cooling rate shows up. Now, this cooling rate does not look like linear, and the reason is because we are looking at very large time scale. So, the x axis or the time axis has been put as a log scale, and that is why this does not look like a linear curve. If I now want to find out how much time it is going to take for the transformation to end, I must calculate on this side. So, let me just take this out. And use now the additivity principle. So, the additivity principle means I have to add up delta Ti upon this. So, now if you look at it, the first interval would be 100, the next interval would also be 100 because it is 200 minus 100, the next one is 300 minus 200 and so on, first one is 100 minus 0. So, if I have to put this formula in here, so I will put this to be equal to, well, the first one is actually 100, I can take it like this, divided by time at this particular temperature, how much time it takes for the transformation to complete, and this time, and we are going to do it for 1% transformation, well, this time is only this much. So, this brings me to a very small fraction, as you can see at the temperature of 726, only a small fraction has gone. Next formula would be add the previous fraction, so that I can get the summation taking place, plus what is delta Ti? Well, delta Ti is H7 minus H6 not multiplied, divided by time for 1%, and let me anchor the column. So, the dollar sign at D, and that is it, this becomes 0.014, and all I do now is simply copy this. So, if I look at it, basically it is showing increasing fraction, and let us see where it becomes 1. Well, it becomes almost 1 here at 3000 seconds, because if I copy this formula here, well, it goes a little beyond. So, as an approximation we can say it takes 3000 seconds for the transformation to complete. Now, what I will do is, we can do this now for different values of B. So, all we would have to do is simply copy these columns to value of B as 50, then 25, 10 and 5, and I already have a calculated sheet to show you the entire calculation in one shot. And you will see this, these are for different values, decreasing values of B, these are the cooling rates, and they are all terminating at the point where the summation term goes to almost 1. Hence, if I join all those with a smooth curve, this becomes my CCT line. So, what this is telling me is this line outside here is 1% transform and this is the corresponding CCT line for 1% transform. So, as you can see, there is a significant shift of the CCT curve from the TTT curve towards the right to longer times, and they are shifted to slightly somewhat lower values of temperature as well. With this, this is how we can convert all TTT diagrams to CCT diagrams, and with this I come to an end to this lecture.